We want to welcome you to our MRI webinar series today. This is JNCI webinar series, and today we'll be talking on a very important topic, which is functional MRI, connecting the mind and the body. And by the special grace of God, our presenter is already in the house, in the person of Professor Godwin Ogbole. Professor Godwin Ogbole is a professor of radiology at the College of Medicine, University of Ibadan, Nigeria, and a senior visiting fellow at the University of Oxford. He is the lead radiologist of the Stroke Investigative Research and Education Network, SIREN. His core expertise is on neuroimaging of stroke, dementia, pediatric epilepsy. He holds a master's degree in epidemiology, clinical investigation and radiation physics with a doctorate in neuroradiology. His recent interest is in MRI imaging analysis techniques using machine learning tools. He received funding from the Engineering and Physical Sciences Research Council, EPSRC, to develop tools for enhancing image quality in low field MRI images, which are very common in Nigeria, and that of children with epilepsy. Professor Ogbole is the secretary to the Faculty of Radiology at the West African College of Surgeons. He has published more than 150 scientific papers with numerous citations. So we consider him to be equal part researcher and clinical teacher, and is especially interested in maximizing and enriching the African Imaging Network through resourceful training. So, ladies and gentlemen, join us to welcome our presenter for today in the person of Professor Godwin Ogbole. Professor Ogbole, please, you can unmute your mic and take it off from here. Thank you very much. If you have any question as the presentation is going on, kindly put up your question on the chat box, and Professor Ogbole will respond to all the questions at the appropriate time. Thank you very much.
Okay, thank you very much, Uche. I just want to confirm if you can hear me, Uche. Just let me know if you can hear me.
Yes, we can.
You can hear me?
I hear you.
And you can see my screen?
Yes, your screen is up.
And it's fine.
Very fine. Thank you, sir.
All right. Thank you very much. Okay. So thank you, Uche. And I want to just thank JNCI for inviting me for this talk. And I'm looking forward for us having a discussion and having a nice time. My name is Godwin Ogbole, and I'll be looking at functional MRI, how that connects the brain and the mind. One of the interesting things you will know, we're going to be talking about the mind and the brain. I just want to use this opportunity to recall a verse from the Holy Scriptures, which says that I will praise thee, that's talking about God, that I am fearfully and wonderfully made. Marvelous are thy works, and that my soul knoweth it very well. This is what we will see as we go in the course of this lecture. So, as a form of declaration, I have no financial interest or relationships to disclose as regard to the subjects of this presentation. And as a disclaimer, I would like to say that most of this talk will stimulate discussion in advanced MRI applications, and it will also consider critical age-long questions about the brain. Hopefully, we'll get some answers. I do not pretend to be an expert on the topic, but I will share some of the assumptions and some of the unknowns, and also share my views, and hopefully we can come together and reach some understanding of how the brain and how the mind works and how imaging has helped us to understand all this. As a form of outline, I'll be looking at neuroimaging as a watershed for neuroscience, and also talk about the structure of the brain and interesting facts of the brain. We'll look how we can find the mind, and also we'll look at what MRI is and what functional MRI. I will try and explain in a brief way how fMRI, that's functional MRI, how it works. And we'll talk about the functions of functional MRI, And we can find a way of seeing how the brain and the mind are connected. And then we can see if fMRI can read our thoughts and our minds. And then we'll look at concepts about neuroimaging and the mind. So just a brief background to tell you about my experiences with MRI scanners. As you know, I'm a neuroradiologist. I trained in Nigeria, in Ibadan, but I've been able to be privileged to work with researchers in Oxford. And this was my first experience with a 7 Tesla MRI in Oxford, understanding that. And I've also worked with a 3 Tesla MRI when I had a workshop also in Cape Town in 2016 with some of my colleagues. And also I've also been exposed to 1.5 Tesla MRI and also a low field scanner. So these are the kind of scanners I've used, and I'm sure most of you use several scanners. Just as a background, the history of imaging and looking at the brain has been a point of interest for so long, since the discovery of X-rays. People have wanted to study the mind, to study the brain, to study how it looks. And this started as far back as 1895, just a plain skull X-ray. And there are several techniques that have evolved over time. And more recently in the 70s, the technique of CT came where we could see not just the bony structure, we could also see the structure, the imaging structure of the brain. And then MRI became a more higher resolution technique that could also make us resolve more of the soft tissue of the brain. And it has also, grown through several breakthroughs. And we have research techniques now that can look at not just the structure of the brain, but can also look at even the axons and how they are distributed within the brain. And also nowadays, even with microscopy and all that, we can actually identify single neurons. And functional MRI is one of the tools that help us also understand how the brain works. And these are the things. So all these techniques have revolutionized our understanding of the brain and how we can better diagnose disease that have to do with neurological conditions, from Alzheimer's to things like multiple sclerosis and several other neurological conditions. So neuroimaging has been the bedrock of understanding neuropsychological or neurological diseases. So to look at the brain generally, the brain is a complex structure. It's highly complex. It's generally divided into 3 parts.
Excuse me, Prof. Your slides are not moving, sir.
My slides are not moving.
Yes. We are still seeing functional MRI connecting the brain. Okay, it's moving now. Thank you.
Wow. No, that's not. I'm going to slideshow. Can you see is it moving now?
Yeah, it's moving now. Thank you.
Can you see the previous slide? Did you see the slide?
We are seeing the complex brain.
Oh, it's not moving. Can you see another slide?
No.
Is it moving?
It's not moving. We're just seeing the complex brain.
Okay, so
we suggest maybe you unshare and share again.
This is not good. Huh?
Okay, it's moving now. It's moving now. We are seeing cortex.
Huh? You're seeing
cortex.
I need to. Hello, can you see any slide?
Your screen is not up yet. Okay, your screen is up now.
Is it okay? It's up now. Can you see my slides moving?
Yes, it's moving now.
Are they moving? It's moving now.
Yes, okay. Thank you.
Sorry. Sorry. So I was telling you about my experiences with MRI, and that's me in Oxford with the 7 Tesla system, also in Cape Town with a 3 Tesla system, and also in Ibadan with the 1.5, and also with the low field scanner. And I just talked about the history of imaging and how neuroscience has helped us. And talking about that the brain is complex and has 3 regions. And then one of the regions is the cortex, the neocortex. And this has various areas that control sensory, motor, and control our thought, our memory. And the wiring is very plastic. But let's look at the frontal lobe, which is one of the biggest, which is the largest part of the cerebral cortex. And the main site of the so-called higher cognitive functions. The frontal lobe contains a number of important substructures, including the prefrontal cortex, the orbital frontal cortex, the motor and premotor cortices, the Broca's area. These are structures that are involved in attention, language, and decision making. We also have the parietal lobe. The parietal lobe is another part of the brain of this neocortex, and it usually helps us to integrate information from the ventral visual pathways and dorsal visual pathways. There's also the occipital lobe. The occipital lobe is the major primary visual area of the brain. It receives projections from the retina via the thalamus, and from where different groups of neurons separately encode different visual information such as color, orientation, and movement. The brain is very plastic, and things like the temporal lobe, contains large amount of substructures and functions and helps us to understand perception, face recognition, and object, and things like that. And damage to any of these lobes can result in disease or cause in terms of being able to have difficulty with recognizing the environment or interacting with the environment sufficiently. The cerebellum is also another part of the brain which monitors and regulates motor functions, and also accounts for roughly about 10% of the brain's weight. However, it contains more neurons than the rest of the brain combined. This is one of the most highly sophisticated parts of the brain. Even though it's about 10%, it's like the neurons there are more than the entire brain combined. And also say that the brain is very plastic in the sense that it can learn, it can use other parts for several functions. The same part can be used for several functions. Now, in terms of dividing the brain into several parts, we have you can divide the brain into several parts, like the forebrain, which contains the thalamus, the limbic system, and the neocortex, which I've talked about. The thalamus is the center that relays, in terms of sensory information. And then you have the limbic system, which is the basic or the seat of emotions. This is what drives behavior. And it contains, and it encompasses several structures, which I will describe. Apart from the limbic, it contains things like the amygdala, the fornix, the thalami, the memorial body, the hippocampus. All these are the structures that contain or make up the limbic system. And this is the seat usually for emotion and for most of the behavior that we have. The hindbrain, which mostly contains of the pons and the medulla, is usually, for the pons, controls maybe different aspects of sleep. The medulla controls our autonomic functions. The cerebellum coordinates movements, as we have talked about. And then the midbrain majorly forms as what you call the traffic cop. It's the one that helps us to filter information so that we can concentrate and do things. It helps us to organize and filter out any information that the other parts of the brain doesn't want to function at that time. Then there's another concept I want us to understand about the left and the right brain. This is really, there's several theories, but talking about the left and the right brain is an oversimplification, which is focused primarily for motor functions, for movements and things like that. Well, however, the brain does not have, what you call like the right or the left brain. But there's a theory, because when you are trying to solve a problem, both parts of the brain are activated. And when you're speaking like language, so both parts of the brain function at the same time, but there's a level of dominance that goes on when people are working. So there's a theory of the left and the right brain, which is more focused on terms of dominance. And people who use one part of the brain, are said to be left brain. People, who are like, more logical, analytical, or objective are said to be left brain, because maybe that part of the brain has been seen to be dominant in those functions. But it's not as if one part of the brain only functions, for one particular activity. So just to get that clear. So there are also some other brain facts I want us to also know. Interesting is that the brain is about just 2% of the body weight, and it becomes fully formed by the age of 25. And it takes about 25% of the body's oxygen and consumes about 750 ml per minute. So the brain has what's called unlimited capacity. It has over billion neurons and more than 1 quadrillion connections. This is to show you the amazing how the brain is connected. So just the surface, looking at the brain alone is not enough. The brain has the ability to learn, and learning also changes the structure of the brain. So structural changes also can also alter the functional state of the brain. The brain can be reorganized, and it develops asynchronously depend on the challenge that it faces. So the alterations that occur during learning can make even the nerve cells more efficient. Just like building your muscle or training yourself, improving your memory. So the brain can learn, the brain can be more efficient, can do more. The capacity of the brain is unlimited. And when the neurons can also become destroyed, when they are damaged or destroyed, become or abnormally formed, they can result in disease. And there are several things. There's no one place within the brain that holds all memories. Different areas of the brain form and store different kinds of memories, and different processes go on at the same time. So the emotional responses, there are certain areas that are more recognized to give out certain brain activity, like the amygdala, which is responsible for emotional responses, or things like the striatum, which is most responsible for memory skills. The hippocampus is known for retaining and recalling declarative memories, and there are several other parts of the brain like that. The other thing about the brain is that you find that the brain starts to remember things even from the womb, and memory can start as early to work as early as 20 weeks of conception. That's one of the interesting things. And short memory only lasts about, so what you decide to recall, we can last about 20 to 30 seconds only. So these are the interesting things about the brain, that the brain is a complex structure, both in terms of, and sleep has been recognized to be able to enhance or be a significant part of memory. And sleep also helps in the retrieval and storage of memory. The other thing I want us to know is that aging, it's not a direct correlate that when you begin to grow old, you'll begin to lose your memory. The brain is equipped to last and to be used. If you do not use a particular part of the brain, you lose that function. And most people who are active in their young age or in middle age discover that they are able to retain more memory, or even short and long-term memory, longer than those who are use their brain less actively. So aging is a concept, does not really affect the brain per se. It depends on how effectively that brain is being used. So I move to the next question of this talk, which is, where is the mind? And these are the things that has concerned a lot of people for several years, over centuries. Now, where is the mind? There are two views. There's a scientific view, and then there's the philosophical or spiritual view. The philosophical or spiritual view says that there is no local, or that the mind is well distributed throughout the body. Or some people even believe that the mind is outside the body. It's outside the body. It's like the air around you. But the scientific view gives us evidence that the mind is within the confines of the brain. And I will tell you why. And because I'm a scientist, what I was describing, I said there are several components of the mind. One of the things we know about the mind is that the mind is composed of neurons and synapses, which are constituents of the brain, the neurons and the synapses, and that there are neural circuits, like I've told you before, that the brain, apart from having 100 billion axons or neurons, it contains about 1 quadrillion of connections. These are connections, and the several are connected by several permutations, which even cannot be resolved even by, I don't know, maybe the most supercomputer may be able to resolve it, but I don't think it has been resolved yet. And apart from that, there are neurotransmitters, chemical messengers like dopamine, serotonin, that are released at different times to communicate a particular message, to deliver a particular effect. So these are the things. When you are happy, when you are sad, these chemicals are released, are given triggers in the brain that allows these feelings to come into fusion. When you are in love, there are certain quantity of these chemicals that are released, or that are commanded to be released by the brain. And then the brain has several regions. You have the prefrontal regions, which mostly controls executive functions such as decision making and planning. And the amygdala is a place for emotions, for fear, for understanding, for laughter, and things like that. And we've also recognized that there are brain waves. Electrical activity can actually be measured from the brain, and this can actually tell us the state of consciousness and the state of wakefulness of a patient or of a person. And we also know that the brain is plastic. It's very plastic in the sense that it can adapt, it can learn, it can recognize and have experiences, and it can also reorganize its neural circuits based on experience, and also is able to function in response to new challenges. So these are the things and all the experiences that we find that we had. All these components are what we consider the components of the mind. But still, people still wonder, that is the mind, is it still physical or abstract? Even in the mind, some people feel that the mind is, somewhere else apart from the brain, that is in the heart, the physical heart that you see. These are philosophical, but there is no scientific basis for putting where all this. So the seat of thinking is where? Is in the brain, is within the cranial vault. Because when you begin to think, I'm sure some of you know that when you begin to think, you're worried about a particular thing, you start to have a headache. That tells you where that is. But interestingly, sometimes when your heart is broken by a loved one, you feel pain in your heart. So these are the kind of things. So sometimes you wonder where the mind is really, because these are things. So the other thing I want to ask is that, can imaging actually demonstrate, apart from demonstrating the brain, are there extra cranial effects or extra other parts of the mind that is not within the brain? That is the question that a lot of philosophers have been asking for years. And maybe as we begin to discuss, as we go into the lecture, we'll see how this pans out. Now, in terms of the brain and mind connection, like I told you, they will have several connections in the brain. And many people have tried for several years to unravel these connections and to say how does the mind and the brain connect? Is there a separation? Well, cognitive neuroscience and MRI supports one conclusion. And what is the conclusion? Is that the brain actually is the hardware, and the connections and the interactions between the neurons and the neurotransmitter in the brain is the software that runs the brain. So the mind has a physical basis, which is the brain, and memory or thought is neither a single entity nor a phenomenon that occurs in a single area of the brain. This is a phenomenon that is diverse. You cannot pinpoint one area. If a particular area of the brain is damaged, another area of the brain can be used to take off that function. And there are several imaging techniques that have been used to look at the several functions, the brain functions, or the functionality of the brain. And one of the techniques is EEG, that measures the electrical activity of the brain function. And this is done real time, and it can be done during sleep or in response to a sensory stimuli. And we know that there are electrical activity that are released during several functions, and the degree of this electrical activity can be measured and then can be resolved to represent a particular or correlate with a particular stimuli. There are other techniques which is called the magnetoencephalography, which is EMG, and it's similar to an EEG, but this measures the magnetic field that is generated around the electrical activity, and this is more specific, and is able to help us to understand cognitive processes such as attention and perception. There's also another imaging technique, which is the diffusion tensor imaging technique. And this measures the diffusion of water molecules in the brain. It's able to help us, give us information about the structure of the connectivity of the neural pathways. And with studying this, we're able to look at the white matter tracts and their role in cognitive processing and our understanding in problem solving and things like that. And also, the other rare technique also, which is not common, but mostly can also help us with understanding brain functions, is the positron emission tomography, which measures changes in the metabolic activity using radio tracers, and glucose. And it's able to help us to understand things like language, attention, and other precision. This is what a positron emission tomography looks like. It measures what? It measures the radioactivity that comes from several parts of the brain when they receive, radio-labeled glucose. And when there's a distortion of this metabolic activity, it can result in disease, which can also be measured and monitored. And then finally, we go to the major thing I want to discuss, which is functional magnetic resonance imaging, which some people have considered the greatest scientific discovery of the 20th century, is functional MRI. Functional MRI measures neural activity, but it does this through a surrogate, which is what? Which is oxygen. So it measures the amount of oxygen within the blood. And this is usually a unit thing that we will discuss as I go in subsequent slides. But the interesting thing is that understanding brain function or understanding brain activity is not just using one technique. Functional MRI alone cannot resolve how the brain works or how to understand all the cognitive processes of the brain. We need to integrate all. So there's a combination. We need to have a combination of all these tools. How does MRI work? MRI is magnetic resonance imaging. It's an electromagnetic tool, and it works by putting a person inside a big magnet. The person, a very big magnet, a very powerful magnet. The body is made up of mostly protons, hydrogen, or mostly hydrogen protons, which is of course contained in water. And when a person is put inside this magnet, these hydrogen protons, which have some magnetic moment around them, which can also have a magnetic effect, they usually align along the with the magnetic field that you've created. And usually what happens to get an image, a radio wave is sent into an individual. And when that happens, this radio waves distort the hydrogen protons in water. And when it distorts them, these hydrogen protons get, after a while, when the frequency is released, it is what? They return back to their normal state. And it's in the return stage that the energy that they release is measured and given a signal. Now, the frequency of the radio waves can be tuned by changing the magnetic field using what you call the gradient curves. And then the frequency changes, the differential release of the proton energy is what creates an image. These are the simplified way of putting how this image is generated. However, it uses complex computer systems to resolve what you call intensity. So several tissues have several amount of hydrogen, and the way the hydrogen returns, for several tissues, for water, for proteins and different things are different. And the computer is able to resolve what is water, what is soft tissue, what is protein, what is fat, and that is what we see after all the arrangement as an image. Now, the difference between functional MRI and MRI are basically that MRI, straightforward MRI, is a structural. Just look at the structure of the brain. That is what the MRI does, and it can be able to tell us where there's a cyst, where there's a tumor, where there's bruising, where there's bleeding, and all that. So a plain MRI measures or demonstrates to us only the structure, telling us what is wrong with a particular part. But functional MRI helps us to understand the activity that are going on within the brain. These are microscopic activity, and it does this by what? By measuring the amount of oxygen. And some people have said that because of that, we are able to be able to see thoughts, see our feelings, and things like that. But it does this through using statistical methods to create a map around the brain. So it measures what? Like I said, it measures the ratio of oxygenated hemoglobin to the oxygenated hemoglobin. And what happens is that when there's exercise, when there's a brain activity, it uses what? Oxygen. It depletes oxygen. And when that oxygen is depleted, the body now produces, or the brain or the body is stimulated to move oxygen to that area. And how it does is that it sends more oxygen that is actually needed. So when there's a brain activity or a particular part of the brain is depleted or is being active and it becomes depleted of oxygen, more oxygen is sent to that region. And because more oxygen is sent to that region, we can measure that activity. And that's what MRI, a functional MRI, does. And because, using several techniques, we can actually color the areas that have that activity using, of course, other computer technology. And the technique for MRI is called what's called the Bold technique, which is what? Which is blood oxygen level dependence or dependent technique, because you are measuring what? You are measuring the amount of oxygen that the particular part of the neural area is using. And when you are thinking about a particular thing, certain parts of the brains are activated. And when it is activated, they require more oxygen. So that is what the computer, and this can be captured every microsecond. That's what makes it unique. And when that activity of oxygen is seen in those areas are lit up. That lighting up are captured through statistical methods, several statistical methods. Like I said, if you look at this image, this is the neurons, and they require what? Oxygen. When they take oxygen, you can see the red areas. These are areas that are using oxygen, and these are the areas that can be measured using what? The blood oxygenating level dependence. And that's what you measure. Once you measure these areas, we can now color those areas in the brain and say, oh, this area has been activated. And then we can know that when a particular stimuli or a person is thinking about a particular thing, the particular brain, the part of the brain that is activated, can create a pattern which we can measure and which you can see and correlate using statistical methods to to represent that particular stimuli or that particular thought or that particular action or that particular cognitive process. So these are measured within small boxes, which are called voxels. So you are measuring the bone signal is coming out from small areas of the brain, and we now measure those small areas to determine what kind of activity is going on. If somebody is listening to music, not all parts of the brain will be lit up. The parts of the brain that are lighted up are the parts that we can say, okay, this represents this type of music. If you listen to reggae music, certain parts of the brain may be lit up, and that may represent reggae music. If you listen to another classic, maybe you listen to classic music, the pattern of oxygen use or pattern of neural activity based on your experience and that may be different. And this is what we measure. And we can do that through using several statistical techniques. The commonest one, which is that says that one part of the brain represents one particular part of the activity, is called the reverse inference. And it's a mathematical construct that just tells you about the measure of brain activity in response to one particular cognitive task. In the sense that if a cognitive process X is engaged, then the brain, this particular part of the brain is active. But that's not the true picture, because we know that several parts of the brain are activated. That brings us to what you call a multivariate pattern analysis. And this is what is a non-modular approach that considers that the entire pattern of activity is over all the voxels happens at once, that several other parts of the brain are being activated through several degrees of activation. And machine learning is what can help us to understand these patterns of activity based on the cognitive processes that are going on within the brain. What can fMRI do? fMRI, which is functional, apart from revolutionizing our study of the mind, it helps us to be able to understand the thought process, how the thought process goes on, what is happening when somebody sees an image, when somebody does a particular function, how do you make decisions and all this. So fMRI is able to not just to show us in terms of physical action or sensory or motor actions, it's able to also understand decision making, emotion, hearing changes, language, memory, self-awareness, navigation. All these are several processes that fMRI can use through research to help us to identify and diagnose or monitor or treat several conditions, because we know what the resting state of the brain is. So fMRI has several other clinical applications. It can be used for diagnosing neurological disease and psychiatric disorders like Alzheimer's, Parkinson's, multiple sclerosis, and several other things. So it can be used for pre-surgical planning, so that the surgeon can know which particular areas are active for a particular thing, and you don't want to avoid those areas, or to also know that if you damage a particular area, the patient may lose those particular functions, and it may also be necessary for counseling so that people can understand the outcomes of treatment. Functional MRI can also be used to monitor the treatment response, to see how the brain activity, can change or is improving. In terms of depression, when you're treating a depressive illness, there's a particular pattern for depressive illness. And if that pattern begins to change, you may begin to say that that particular treatment is working. And of course, functional MRI is being used extensively for research to help us understand the brain even more, because right now we still do not understand how a lot of things happen within the brain, how people respond to disease, how one particular patient may respond to a particular drug treatment, another patient may not respond, and how people think about certain things, and how people use their brain, to retain certain memory, how aging affects us and all that. So research is going on, and functional MRI is the tool. But the thing to know is that functional MRI is just one in the toolbox to understand brain function. And there are several studies that have been going on. But the key thing is that since the brain is complex and interconnected, all the regions are interconnected, we need to harmonize all the imaging techniques. Apart from functional MRI, use DTI, positron emission tomography, EEG, MEG, put all these things together to fully have the best picture of how the brain functions, or how the brain works, how to understand, the mind, which is the interconnections or the interactions within the neurons. Because the interactions of the neurons are what gives us to understand attention, perception, and things like that. So the integration of data, the clinical data we're able to harness from all these imaging tools, putting together and putting them side by side with genetic and behavioral and cultural data, helps us to better demonstrate or represent a particular brain function. So it's not just a direct correlation of when a particular part of the brain is activated, it means one thing. No, you require data. You require to understand the behavioral, the training, or the background, the cultural background of a particular individual. And this is done by collecting, information from large cohorts of people. And that's what neuroscience has done and has doing in certain things. To just tell you a little bit about people claiming, there's a BBC article that claimed that fMRI can now read the mind, not in its entirety. It can give you suggestions. Maybe in the next couple of years, when we can integrate newer or more advanced techniques, or we know that the brain can actually help us to understand, how the mind works, what is going on in the mind of an individual when he's being imaged, based on what his behavior or his past, his cultural things, and then based on patterns that have been recognized in the past, statistical patterns that have, or data that has been obtained over the years can be used to correlate and say that this particular person is thinking about a particular thing. But reading of the dreams is not a full science yet, but there's a possibility that it may occur in the future. One of the problems that this is difficult reading the mind is that because one of the problems with fMRI reading the mind is that when not all areas of the brain, that when you are doing fMRI, certain areas of the brain are not activated, but they may be what? They may be active, in subtle ways. So this measure of, and what we're just doing is getting a statistical, package of what the information that we have, because sometimes we're not getting all the information, and that's why functional MRI is said to that it can detect areas of the brain that are active during different mental activities, but cannot photorealistically record thoughts or dreams, because there are several other things that are going on. Also, we also know that apart from functional MRI, there are things like what you call diffusion tensor imaging, or things like diffusion weighted imaging, other things that also help us to understand differences. And then one of the things that help us to look at these differences is the Human Connectome Project, where they have collected data from about 1,200 subjects, and they're looking at the interconnections or the variability between people of different races, people of gender, people of different gender, people of different ages. And this helps us to better understand how these interconnections, how they work. And you will also see that people have also gone ahead to look at structure of the brain. And there's a controversial study that talks about the brain size. That if you have a bigger brain, most likely you have a bigger IQ. Or this has been debunked over the years. And this study was one of the studies that came up and said, look, since the Europeans have bigger brains, they are more intelligent and all that. But we have been able to know with neuroscience and several other studies that these are not entirely true. That the brain of every human being is basically the same. But it depends on what it's able to be exposed to, how that brain has been trained to learn, how those connections have formed over time will determine its level of intelligence, will determine, how it operates. So the brain in terms of structure is the same. And you find in terms of people have used race as a construct to divide. But what happens is that the brain of a black man is similar to the brain of a white man. But even among races, you find out that people are genetically diverse, even among races. So you find out that a black man may be more different than another black man compared to a white man. So the genetic basis of race is a social construct. So it does not have nothing to do with the brain. So in terms of future advances, scientists are now planning to use machine learning and, of course, AI to be able to look at how they can begin to read people's thoughts, read the patterns of the brain based on collecting huge data. Because when you are thinking about a particular thing, certain areas of your brain are activated. And if 1,000 people have the same kind of activation, that means those particular parts of the brain, and they're from the same environment, they have the same experiences, that we can conveniently say that those areas represent this particular thought. And then we can do what we call reverse programming, and to say that when you see this pattern, it represents this particular kind of thought. And that is where machine learning will come in, and artificial intelligence can help us take the information and reprogram it and begin to tell us what we are thinking of, what you are thinking of, how the brain is working, and be able to code what you are thinking at any particular time when you're under the machine. So it is possible that in the future, we may be able to use this functional MRI to be able to read thoughts, read dreams, and then several studies have also been done to say that, look, they've looked at the brain pattern of people that become suicidal. Take a group of people who have suicidal thoughts and a group of people who do not have suicidal thoughts, and they studied their brains, and they discovered that the brain pattern in terms of when they are exposed to a particular stimuli, when they are exposed to things about death, that the way the pattern of the brains of those who have attempted suicide or who have suicidal thoughts, the way they respond to that event of death is different. So we can also use this kind of pattern, recognition to begin to identify those who may likely, want to commit suicide in the future, or who are likely to benefit from treatment for psychological treatment to make them avoid suicide. And these are studies that have been done, and several other studies are going on to help us understand the pattern of the brain. And functional MRI produces or provides a significant or unique basis to be able to understand this. So in conclusion, imaging advances have greatly increased our accuracy in understanding the brain functions, and big data and artificial intelligence can help imaging to do a better job. And it may be possible to download our thoughts in the future, maybe in the next 20 years, who knows? The brain is the home of the mind. This is a scientific conclusion, that the mind is housed within the brain, and that the capacity of the brain is limitless. And of course, we also know that it's still a matter of great research because of its complexity. Thank you very much. I also just want to acknowledge my teachers, my collaborators, my people from Oxford, from Nigeria, and of course, thank JNCI for giving me an opportunity to contribute to the body of knowledge amongst, at least, especially those of us in Africa who may not have access to most of this advanced technology. But I can tell you that things are moving, and those of us who are involved with MRI science and things like that are looking for ways to bridge the gap between the two, the North and the South. Thank you very much. So I will look forward to having your questions.
Thank you very much, Professor.
This is the hospital where I work in UCA. This is in Ibadan. It looks very regal and beautiful, I think. Thank you very much.
Thank you very much, Professor Ogbole, for a wonderful presentation. It was actually on point. So probably before we go further to ask questions, I have my own question that I want you to respond to. Then while we read out some questions that are already here from some of the participants. Meanwhile, before I go into that, I want to first of all appreciate three very important persons here. Very important because they were the early birds in today's webinar presentation. OT, that's the username, I don't know the name in full. Then Olaniyo Olubemi and Wisdom Major, for they were the first three persons to join this webinar. I want to appreciate the three of you. So before we end, we also appreciate some other people that will recognize their presence here. So now the first question I want to ask Professor Ogbole is, in functional MRI, can functional MRI give us an idea of somebody's emotion at a particular time? What I mean by somebody's emotion is if somebody is afraid, in love, or just things like that. Maybe is there a particular brain pattern that we notice when somebody is angry, when somebody is anxious, when somebody is happy, when somebody is sad, and the rest of them? Thank you.
Okay. All right. I think that is a very simple question, and the simple answer is yes. That's like I think it's one of the commonest things that we've been able. Like I said, there are certain areas of the brain, the seat of the emotion, the amygdala, the limbic system of the brain that I've discussed. These are areas that are lighted up. The signals, we can pick signals. So, and it can help us also to understand mood changes. So you can know when somebody is happy, when somebody is angry, when somebody is afraid. These are things that we can actually, functional MRI can deduce. But it's not just from just one study. It's from understanding what the resting state of that patient is, or that particular person is. You have to understand what the resting state of that person is, and then you also have to use that in context of the data that has been generated from that person's environment. You understand? So it's not a direct, but it can be done. Or if in terms of the possibility, yes, fMRI can do that. Can tell you when you are happy, when you are sad, when you are angry, when you are afraid. fMRI can do that by using statistical methods and things like that. All right.
Okay, thank you very much for the response. So we have some questions in the chat box here. The first question is from Dr. Irene Wangwo, and she's asking, can functional MRI be used to prognosticate in coma patients?
Can be able to use to prognosticate what kind of patients?
Patients in coma.
Oh, patients in coma, to be able to prognosticate when they will wake up. That answer will be yes and no, because like I said, this is not a perfect science. You need fMRI is one technique, but you need several other activity. Now, when somebody is in coma, a lot of things are going on, and you can measure the brain activity. You can measure what the neurons that are active or at a particular time. So if more activity begins to, you monitor that patient over time, and you see that over time, the activity of the brain beginning to respond to small external stimuli, that suggests that this person is likely going to become awake within a particular time. These are things that can be calculated or has been calculated, because you can actually measure, in a person that is in coma, you can measure how he responds to several stimuli, to music, to sound, to person's name and all that, and which part of the brain are active. But in terms of determining exactly when the person will wake up, it may not be, well, I think statistically it may be possible, but like I said, it's within the window of probability. But in terms of using imaging tools or imaging techniques, like I mentioned, EEG, to look at the electrical activity of the brain, to look at other techniques, like the EMG, the MEG, that can also help us to accurately tell if there's improvement in the patient's wakefulness, to be able to determine how awake that person is. But to say when exactly you wake up might not be entirely, but I mean, within certain level of confidence, you may be able to prognosticate, yes.
Okay, thank you very much, Professor Ogbole. Then there's another question here from Adewale, and Adewale is asking, please, what is the difference between DTI, that is diffusion tension imaging, and functional MRI?
Okay. Now, DTI actually helps us to see and follow the patterns of axons, the neural pathway, to see axons, to see how they are distributed, or how it's also, DTI is another form of structure. It's looking more of the structure of a particular or certain part of neurons that perform a particular function. So if a particular neuron is a motor neuron, or what we call fiber or neural tracts that do a particular function, you can actually determine those tracts and see where they come from, or where a particular message starts from and ends. So it's looking at the pattern of those neural those nerves that are involved in a particular activity. Functional MRI, in the other hand, does not. It looks at more of a global thing. It looks at more of the neural electrical, not necessarily electrical now, but neural activity based on oxygen consumption. And we use several imaging techniques to color them to say those areas that are activated. So DTI measures what? Neural tracts, while functional MRI measures neural activity in terms of how much energy they are consuming at a particular time.
Okay, thank you, Professor Ogbole. We have somebody who is raising his hand. Echozona Nelson, please, can you unmute your microphone and ask your question? Echezona, can you hear me? Unmute your microphone and ask your question, please.
Okay, I can't hear anything.
Okay, I can't hear anything. Okay, maybe you just put your question in the chat box while we take other questions in the box. Then there's another question here from same Dr. Irene Wanko, and her question is this: how old is functional MRI, and could it be possible that functional MRI technology is already being employed in artificial intelligence?
Okay. Well, functional MRI, I would say, has been in existence now for maybe close to over 20 years, and it has evolved, and I must say, geometrically over the years. And I'm sure you know that artificial intelligence has been explored in all areas of science and human endeavor. So definitely the artificial intelligence tools or machine learning tools that we have currently will greatly enhance the capacity of us being able to use the tools of functional MRI. That's why I said the tools, functional MRI is still not a routinely used clinical tool anywhere in the world. It's still not a routine, it's still a selected, very few selection. And mostly it's still an area that is mostly used in research for studies to understand several techniques on how several drugs or how several diseases are going on. So it's not relatively a common, has not really been a very common tool. It's a research, majorly still a research tool, and used to be able to understand disease processes and psychological conditions, majorly, mostly cognitive abnormalities and things like that. Artificial intelligence, because artificial intelligence uses huge data, it can help us enhance and improve the quality of our understanding of those patterns of activity. So those two are going to work hand in hand going forward. I believe that in the next 10 to 20 years, the ability of the kind of functional MRI will become more, more available, even in places like Nigeria and places like Africa, because of the tools of artificial intelligence to make these things more efficient and more available in places like Africa and things like that. So I'm confident that, going forward, artificial intelligence can improve the tools or the functionality of functional MRI.
It's okay. So another question from Faith Olushego is asking, is functional MRI the same as bold imaging?
Well, bold imaging is a technique, is the primary technique that is used to acquire the signals in functional MRI. And bold just means, blood oxygen level dependence. That what bold means is bold imaging. Bold imaging is basically the tool that is used to display the signals you see in functional MRI.
Okay, thank you. Then Jibowu Olufemi is asking, what is the role of functional MRI in autopsy? Or I think I can rephrase it. Does functional MRI have any role to play in autopsy?
Like I said, never say never. But what happens that functional MRI does is to measure neural activity. I think in the sense that it is possible that if you want to check somebody, if you want to truly check when the neural cells actually die or begin not to function, you can put a patient inside a machine and see if there are still neural activity going on. But I do not think it has any routine or it's for science. Like I said, it's an ongoing thing. But I don't think there's any clear path of using functional MRI in autopsy. I don't think there's any clear path. But never say never. We never say. But what functional MRI does is to measure or demonstrate the patterns of neural activity that are going on within the brain. If the brain is dead, all the neurons are quiet, you are not likely to see any activity. But when you are asleep, there's what you call resting state MRI, resting state functional MRI. When you are asleep, you'll be surprised that there's even more activity going on in your brain than when you're even awake sometimes. depending on your state. So the resting state sometimes can be when you're having dreams, several parts of your brain can become so active because you are seeing your brain is reviewing and, is the activity that can be measured, that can be assumed to be going on when you are dreaming. But when you are dead, everything is zero. There's just like having an ECG. You have a flat line. So if you put a patient that is dead inside, that is confirmed dead inside a functional MRI, you're not likely to get any signal.
Okay, the next question is from Samuel Chukwemeka Okorafor. He is asking, can functional MRI be used to ascertain if someone is saying the truth or not? So could it be the technique that is being deployed in lie detector?
Well, I can tell you for a fact that people are exploring that. And when I met with one of my hosts in Oxford, he was working. Interestingly, he had an opportunity to work with the NIH, and he told me that people asked that same question. They were trying to see if functional MRI could. That was when functional MRI was just coming into being. If the tool to detect that is possible, you can never say never, but I don't think currently there may not be a standard to be able to detect whether somebody's lying or not fully or clearly. It can tell exactly what somebody is thinking, or give an idea of the pattern of how the brain works, but there's a possibility that it may be able to in the future be able to tell us when people are lying, how their brain works, or how because there are several techniques that people can trick people to believe anything. But I don't think there is a clear-cut technique now that can be used to detect lies with functional MRI. But people are working on it. I can tell you that.
Okay, thank you very much, Prof. So I'm going to take the next two questions together because they're almost saying the same thing. First of all, I want to appreciate the next person that asked question in the person of Dr. Cecilia Moshuka. That's the MD of Jerafa Medical Center in Ibadan. You're welcome, ma. So her question is this: when do you need to request for functional MRI? And the next person, Mr. Chike-san from NMPC Hospital Abuja, is also asking, is functional MRI currently being employed or deployed in Nigeria for medical diagnosis? Thank you.
Excellent question. Thank you so much for that question. And also, thank you also, Dr. Amoshuka. That was one of my mentors and teachers. Okay, so just a quick one is that right now, I'm not aware of any center in Nigeria that does functional MRI. I know of centers that do functional MRI and mostly for research reasons in South Africa. And possibly also, I'm sure there are centers that in Morocco, Tunisia, that they use functional MRI primarily for research and things like that. Because nowadays, because of the available technology that we have, most people want to do functional MRI using a 3T system, even though you can do it with a 1.5 system, but it's more sensitive and all that. So functional MRI is primarily, like I said, is still a highly, like I said, maybe like 60-70% of the time a research tool. But it is used mostly for people who have cognitive. You are worried about, you want to know about people who have been treated for cognitive abnormalities like dementia, people who have problem with depression, with Parkinson's and all that. So we want to be able to monitor, the improvement of those people's status. So in the terms of the request, is mostly for if a neurosurgeon wants to go and operate a patient and wants to find out which part of the brain is the dominant hemisphere in terms of his cognitive abilities, in terms of being able to use or live naturally. You want to be able to see how the brain works and which area to avoid. So for neurosurgeons, they may want to request for to just look at the pattern of the brain and see what the outcome of the surgery may be, and understand that. Then for people who are psychologists and things like that, who are treating people for depression, they understand, or people who are suicidal, you now may want to see how the pattern of activity going on in the brain, and you want to see how your treatments are being how the patient is responding to treatment by doing follow-up, to check out his neural activities, or you are giving a particular patient certain drugs that can actually distort or change the pathway of how the neurons work, like neuropsychotic drugs. When you do that, you can request a functional MRI to monitor treatment, and then also sometimes, not necessarily for diagnosis now, but mostly for diagnosing treatment. So functional MRI is majorly for clinical use, mostly for monitoring treatment outcomes and also to plan for treatment planning. Thank you. That's when you will request for a functional MRI.
Thank you, Prof. So the next question is from Echazona Nelson Ekechukwu, and his question is, what is the advantages of functional MRI over fMRIs? I think that should be like fine needles and things like that.
Yeah. FNS. Yeah. So that is functional, what do you call it? Near field spectroscopy, and that is another technique. It's another MRI technique, or infrared technique that is used to be able to study metabolic activity in the brain. It's all, like I said, there's a combination. These are mostly studies that look at metabolic activity. The fMRI looks at more of neural activity, the firing of the nerves, the firing of signals, and that is it. But like I said, all this can work in combination to give a more holistic picture of what's going on in the brain. One tool may not give you a what you call, like patients with epilepsy. Patient with epilepsy, you can, look at their resting state MRI, and actually you find out that there are certain parts of the brain that are abnormal, or giving you abnormal activity, or when they are responding to a particular stimuli and things like that. But in terms of fMRI, it's not. fMRI has some delay. It has what you call, it has some spatial, relevance. But in terms of temporal relevance, what you are measuring with fMRI is slightly after the fact. So when you are thinking of something, it generates a particular signal, but by the time you are catching the signal, it's like a few seconds late. So you sometimes need to combine all these tools to be able to come up with a holistic way of how the brain is working. So there's a difference between the functional MRI and fMRI, in terms of measuring the metabolic activity during a particular process or during a particular stimuli. You understand? But fMRI is much more of measuring, of the metabolic activity, while fMRI measures more of neural activity.
Okay. That takes us to the next question from Godfrey Luntzi and Obi Indubisi. They are asking same question, and their question is, what is the minimum field strength that is required for functional MRI?
Well, if you say minimum, I would say it's a 1.5. The minimum is a 1.5. That's the minimum. But the best is a 3 or a 7 Tesla. That's what you will get. The minimum, you can use a 1.5. That was what was started with. Most people started with 1.5. Most started with 1.5. But right now, you can. I don't think anybody would want to do a very well-resolved functional MRI that will use 1.5. So, but with 1.5 you can, but still the best would be either a 3 Tesla or a 7 Tesla.
Okay, thank you very much, Prof. We've almost exhausted all the questions, apart from the question from Ijo Fochidima, who is asking of the role of statisticians, the role statisticians can play in functional MRI as they are developing some interest in neuroimaging. So, well, I don't know, Prof, can you just tell us what role statisticians can play in functional MRI development, as it were, for now?
Oh, wow. No, they have a major role because, like I told you, it's a statistical construct because they are interactions that are going on, and what you need, like I said, you have is a statistical model that is formed when those signals are firing at different times, and you need to resolve them and then predict what a particular signal will look like, or a particular stimuli will generate. So statisticians have a huge role, and statistical models, like I told you about AI algorithms, can now be used to predict, patterns from using large data. If you study a particular patient, if you study the brain of a particular patient or a particular group of people and how they think, over time, you can predict how they will react when they are exposed to a particular stimuli. So statistics has a major role in terms of predictive analysis, or deductive reasoning, to be able to help us to, resolve the signals we are getting from a functional MRI.
Okay. Thank you very much, Professor Ogbole, for this wonderful presentation. I'm sure our listeners today are very excited having you around to talk to us today about functional MRI, and I must have to confess that you did a great work in this presentation. For our teaming viewers, I would also confidently tell you that JNCI as a company also have equipments, MRI of 1.5 Tesla, 3 Teslas that can do functional MRI. So I'm sure that by the time we start deploying some of these technologies in Nigeria, the JNCI will also be at the head of the team and leading as we always lead in the field of medical imaging. So with this, I want to appreciate some persons here who we are supposed to at least have a mention of their names. We've already appreciated Dr. Amoshuka. We also want to appreciate Professor Donald Nze from University of Ilori Teaching Hospital, one of the foremost radiologists in Nigeria. And also some of my friends who all the way from the United Kingdom joined this presentation. Ifoma Val Eze, Ndubisi Obi, and Mr. Paul Awa. You are all highly appreciated for joining us in this webinar. And before I finish, I want to also appreciate my colleague in JNCI, Omoshola Ubokoyi, for joining us today and ensuring that this presentation is hitch-free in every ramification. And one of the persons that asked a lot of questions today, which means she was very active in this presentation, in the person of Dr. Irene Wankwo, my beloved wife. I want to thank you for your usual support every time your husband is in the hot seat. Thank you very much. And from JNCI, I want to say thank you very much for joining us in this webinar, and be open to more webinar invites from JNCI, as we are always prepared to give you the best of webinars to ensure that you are brought to par with the recent happenings in the field of medical imaging. Thank you very much, and I call it a day for today. God bless you all. Bye.